Hi there and welcome to Workshop 3. So in this workshop I'm going to load up Lab 3. We're going to be looking at missing values and what we can do to maybe fill them in, which is called imputation. And you'll notice when I open this it says that I need a range of packages, Knearest, Imputation and 2 others required. So I'm just going to click install and let it do its thing. This may take a little bit longer on my machine than on others because I'm on a Linux box, so these are all going to be built from source, which may take a little bit of time. If you're on Windows or on OS X, then it will install pre-built libraries, which will be much faster than it is here. But you see it doesn't really take that long to build most of these packages. Okay, and we're going to look at some data sets here called the husband's data set and the yeast data set. So let's load this first code block in. Okay. Right, so we're going to start with the husband's data set, which you'll see has 199 observations of 5 variables. Okay, and we can see here that when we look through it, we have pairs of couples, husbands and wives that are married. So we have their husband's age in years, we have the husband's height in millimetres, we've got the wife's age in years and the wife's height in millimetres, and we've also got the husband's age when they were married. So you would expect that the husband's age and the wife's age would be somewhat correlated, but that the husband's height and the wife's height may not be. And you'll also note as we take a look, we've got this entry here 99999. Which is obviously incorrect for the age. Okay, so it's very likely that that this is actually a code for missing values. So this is something that used to be done a lot, and it isn't fortunately done all that often anymore. That sometimes you use special numbers to code missing data, and that was done really at the time because software could really only deal with numbers. Whereas of course now we're quite happy to have a blank entry. So this is really a thing of the past, but nonetheless you still find data sets where this is the case. So for example, if we summarize this using the skim function from the skimr package, the skim function just basically skims through the data and gives us a summary of all the variables. So you can see that we've got 199 rows on 5 columns and that 5 of them are numeric, and then it summarized the numeric variables. Here told us how many are missing, which is 0, because they're all full of numbers, so the completion rate is 100%. It's then given us the mean, the standard deviation, the minimum, which is the 0th percentile, the first quartile, the median, the upper quartile, and the maximum. And it's also given us a histogram of the variables as well. And so we can see here that there's 9999 in 2 of the columns, the wife's age column and husband's age at marriage column, and therefore the means for these are completely silly, right? So the average age for the wives is apparently 1492 years old, and the husband's age at marriage is 226. So this is clearly not the case. So we've got to convert these 9999 values into proper missing values. So the Narnia package is contains a bunch of useful things for dealing with NAs, which are missing values, thus the name. And the replace with NA function is replaces a specific value with NA. So you can punch in 1 or more values in that column to replace with NA. So you can see here we're taking our husband's data, we're piping it into the replace with NA function, and we're telling it to replace the entries in the wife's age column that are 9999 and in the husband's age marriage column that are 9999, and it's going to replace those with NA. So if we run that first line, we'll get the husband's NA data set. If we have a look at that, we can see that entry that was 9999 is now NA. Okay, so when we skim the husband's data, we find that now there are 29 values missing in the wife's age and 4 values missing in the husband's age at marriage. So those are the completion rates, right? So we're 85.4% complete, so around about 15% missing data in the wife's age and just 2% missing data in the husband's age at marriage. And now, of course, those means are reasonable and the distributions are now reasonable as well. Okay, so now we're going to have a look for ourselves at the yeast data. So let's run skim on the yeast data. Now this is going to take a wee while because the yeast data's got rather more columns. So we've got 81 columns, 2,500 rows, 2 are of type character. So that's the ORF, which is the gene name, and the name column. And you can see that the completion rate for the numeric variables are all 100%. Okay, and the means are often very large, except for these two, which are a lot lower. Okay, and these are, but you can see overall the maximum for just about every column, in fact for every column, is 9999, which is much higher than any of the other values. In fact, this is normalized gene expression data, so the mean should really be close to 0 for all of these columns, and instead the means are very much non-zero. So we're going to do the same thing here. So we're going to replace them, and we could use the same code that we did before. So we could take that same code that we did before and replace with NA, and then we'd have to use each of the column names. So for example, we could use alpha 0 in here and alpha 7, say, and it's 999 that we want to replace, and alpha 7. So if we do this, so we take the yeast data, and we're going to get another data set, yeast NA. So if we do that and then we skim the yeast NA data, then we can see we fixed up those first two columns. So now there's 57 and 62 missing values together, respectively, and we can see their means are much closer to 0. Okay, and their upper limit is now sensible, and now the histograms look somewhat sensible too. Right, previously everything is skewed to the right because all the data is actually bunched down near 0, and then you've got this 999 entries, which is making the histogram look very odd. Now we could do that, but we'd have to do it with all of them, which is going to get a bit much to put on that list. So the other function we can use is replace with NA all. So let's try that instead. Okay, so because there's a consistent value across all of them, we can use replace with NA all. Okay, and you can see that that takes a condition argument, and the condition argument is gives us an example here. Okay, so we can see that here our condition argument should be something like, so let's have a look. So here's the syntax. So this is what's called a lambda function. And it's basically a lambda function is basically what's called an anonymous function in computer science. And essentially it's just a way of defining a function in a very small footprint, basically. So the tilde defines the function, and then .x is the thing passed into the function. And so we've just got a condition here such that anything that we pass into the function that is less than 20 returns true. So we want anything that is equal to 999. So anything that satisfies that we want to replace with NA. So if we run that and have a look at our yeast NA, we can see that all of them have been replaced correctly. So now we have quite a lot of missing data in some of those columns. But the overall amount of missing data, because we've got lots and lots of rows, the overall amount is about 2% or thereabouts. You can see that those distributions now look sensible. Okay, and the upper values now look sensible as well. Okay, so two ways to do this. If you've just got one or two columns, replace with NA, and you just give the name of the column and the value you wish to replace, or more than one value. You can put more than one value in here if you want. Or we can do it all at once with replace with NA all. Okay, so now that we've got our NAs, we'll just put the skim down here so we can see where it is. Again, here we go. Okay, so now that we've got our data full of NAs correctly, we can now look to see how we can play with that type of data. So the first thing we might want to look at is we might want to look at where the missing values are. Okay, so the Narnia package contains a bunch of options for visualizing where our missing values are. And this is important because the type of patterns that we see in the missing data can give us a bit of a hint as to how the data being missing may have arisen. Okay, in particular, we're wanting to distinguish there's essentially three types of missingness. There's missing completely at random, missing at random, and missing not at random. By visualizing the data, we may be able to figure out whether the data are missing completely at random or perhaps are missing at random. Now, the difference between those two is missing completely at random means that the missingness is scattered fully randomly across the data. Missing at random means that the missingness does not depend on the values that are missing, but may depend on the values that are present in other columns. So, for example, perhaps the pattern of missingness depends on the husband's age. For example, in the husband's data. So perhaps the wife's age is missing, where the husband's age is particularly young or particularly old, perhaps. Okay, or the wife's age could be missing just randomly. Okay, so vis-miss helps us visualize the missing data. So this just helps us visualize across all of the rows and across the columns, where do I have missing data? So you can see that I have most of my missing data in the wife's age, and it's relatively evenly distributed along the rows. And I've just got the odd value. I think there's about 4 of them missing in the husband's age at marriage data. So vis-miss just shows you where your missing values are in relation to the rows. We can then perhaps zoom in to find out just how many of these are missing. We could filter where the husband's age is married and is where the husband's age at marriage is missing, just to zoom in on those rows. And we can see that when the husband's age at marriage is missing, the wife's age is missing in 3 out of 4. Now that could just be chance, but it could also be hinting that maybe there's something missing here. And in particular, we wouldn't be able to use the wife's age in order to try and figure out what the husband's age at marriage is, because we know that we actually only have one value for the wife's age that is non-missing anyway. So maybe we could use the data in these 4 columns to impute this one, but we can't use the data in the wife's age column really to impute these without first imputing the wife's age. Okay, right. Now there's another couple, so there's Gigi Misvar. Let's see what that does. So this is basically the same thing. Instead, it just visualizes how many missing values you have. So we've just got the number missing and a line showing you where they're missing, and then Gigi miscase shows you essentially the same thing, where except for rows instead of columns. Okay, so Gigi misvar is for your columns, so how many missing values are there in each column, and ggmiss case is how many missing values do you have in each row. So you can see that I've got 3 rows here at the start where I've got 2 missing values, and then a bunch where I've only got 1 missing value, which will be the wife's age, and then a bunch where there's no missing value at all. Okay, so that gives you a sense for how much data you have that is complete versus how much data you have that is incomplete. Okay, and finally, there's the ggmiss upset, which allows you to see the interactions. Okay, so what this shows is it shows you get a bar for each possibility of the various variables being missing or not. So in our case, there's only 2 variables that have missing data. So either the wife's age is missing, or the husband's age at marriage is missing, or they're both missing, or neither of them are missing. Now, we don't care about the case where neither of them are missing. We only care about where at least one of them is missing, so there's only those 3 possibilities. The husband's age at marriage is missing, of which there's 1 with only that option. So this dark dot here represents missing, and the light dot represents not missing. So that 1 there is where we've got the husband's age at marriage is missing, but the wife's age is not missing. Then we've got a big bar here, 26 observations where the wife's age is missing, but the husband's age at marriage is not missing. And then we've got 3 where both are missing. Okay, so this is called an upset plot. And it's a way of plotting combinations of variables, essentially. So if you had more variables here, then you'd have, the combinations of just 1 variable missing, 2 variables missing, 3 variables missing, and so on. Okay. Right. What about relationships? So one thing we might want to check now is whether or not the missingness in the wife's age depends on some of the other data variables we have. So this is to distinguish the case between missing at random and missing completely at random. So let's have a look at this one. So you can see here that we're plotting the husband's data with NAs, and we get a complaint from ggplot that it's removed 29 rows which contain missing values, which makes sense, right? You don't have either the x or y coordinate for 29 values. So that would be the case where we know the husband's age, but we don't know the wife's age. So we don't know where those points would lie on the plot. Okay, so, but we can see that husband's age is a fairly good predictor of wife's age, right? There's a fairly linear relationship between the two. And while you get some outliers here, generally the wife's age is relatively predictable from the husband's age. Now, we could also visualize where the missing values are because we know where the husband's age is for those values for which the wife's age is missing. So the geom miss point takes the exact same syntax as geom point, but this time it takes care of the missingness. So this plot here, you can see that in the blue color here is the exact same plot that I had before. That's all the data that's not missing. And then the red points along here are the husband's age for where we don't have a wife's age, right? So they're not up here because we don't know what the wife's age is. So they're down below the data so that you know that the wife's age isn't actually less than 15. So that's just an arbitrary number that it's put them on, and it's just scattered them around some value below the real data. And what the key take-home message here is that the missingness doesn't seem to depend on the husband's age because it's relatively evenly scattered across the various husband's ages, right? If all of the red points were down here, then we would conclude that the ones that are missing, the wife's age, all have low husband's ages. So that would suggest that the wife's age isn't missing completely at random, and instead the missingness depends on the husband's age because all of the ones for which we have missing data are ones where the husband's age is small. Similarly, if it was all the way up here, right, we'd conclude the same. But because it's scattered all the way across the range of the husband ages, we'd conclude that the missingness here is probably missing completely at random. It doesn't depend on the husband's age as to whether the wife's age is missing or not. And the good news is then that we can essentially use the husband's age to try and infer what the wife's age is in that case, right? If they've been all scattered down the bottom here, then it would be hard to use the husband's age alone to infer what the wife's age is, because the ones that are missing are the ones that have very low husband's age. So we couldn't use the information from the high husband's age to try and infer the information about the missing ones, because the missing ones all have low husband ages. Okay, so because it's scattered relatively randomly across here, we can use the husband's age to try and infer what the wife's age might be. Okay, and we could do the same thing with the husband's age at marriage and the wife's age, right? So we'll do that same set of code there, and now we're trying to see whether the husband's age at marriage might tell us something about the wife's age. Okay, so now we have missingness in the wife's age, which are these ones across the bottom here, and we have missingness in the husband's age at marriage, which are these ones up here. So these 3 points down the bottom here that are clearly to the left of the data in terms of the husband's age at marriage, and to the left of the data in terms of the wife's age, they're the ones that are missing for both. Okay, so what we notice here, this doesn't seem to be a trend between these two variables, and again, the husband's age at marriage is relatively, the missing wife's age are relatively random compared to the husband's age at marriage, because the data here is scattered about the same as the data up here. Okay, so the husband's age at marriage is probably not a useful variable to try and use to figure out what the missing wife's ages are, because there's no relationship there. Okay, but nonetheless, the missingness in the wife's age doesn't seem to be biased to the values where the husband's age at marriage is very small or very large. So again, pointing to the wife's age being missing completely at random, right? We don't have suppression of the wife's age dependent on the other variables that we have. Okay, let's have a look at the yeast data. Now the yeast data is very large, so we might not want to look at all of it at once. Let's give it a go just in case, see what happens. Let's vismis, oops, on the yeast NA data. This will probably take quite a while, because we've got 2,500 rows. Oh, it didn't take that long. 2,500 rows and 80 odd columns. And you can see here that the missingness does seem to be relatively randomly scattered throughout the data there. Okay, there's no obvious patterns. So the patterns that I'd be looking for are vertical stripes. So if I had a vertical stripe, then I've got a lot of missingness in one particular variable. Or horizontal stripes, where I'd have a lot of missingness in one particular observation. But that doesn't seem to be the case. It seems that the missingness across this data set is relatively uniformly scattered. If, of course, I did have a column that had a lot of missing data in it, then perhaps it wouldn't be useful to deal with that column anymore, and the best thing to do might be just to delete it. Similarly, if we had a lot of some rows that were missing data across a lot of columns, then it might pay just to remove those rows from the data set, right? So dealing with missing values, we can often just remove rows and remove columns in order to reduce things down. Now, in this case, all of the columns have missing data except for these two on the left, which are character columns, which are just like naming what the rows mean. So removing any column because it has a missing value is going to be useless, because we're going to be throwing all the data away. And similarly, my suspicion is that most of the rows probably contain some missing data. Let's have a look. Right, we could do the viz miss. Now it was GG, wasn't it? GG miss cases and GG miss var. So there's the missingness in the variables. So you can see that all of them have some missingness. The one that of the numeric message, the only two that don't have anything missing are the name columns. And so one of them has at least 16 missing, and one of them has over 100. So removing columns that have missing values, the columns have at least 15 missing values, each of them. So it's fairly hard case to say that we should remove specific ones. What about cases? Okay, we can see that almost all of the data, about 75% anyway, has at least one missing value. So if we were to only keep records for which we have complete data, we would be reducing the size of this data set down to about 20% of what it actually is. So that's probably not an option either, right? Because we're basically throwing 80% of our data away. Again, we can't remove the columns because all of these missing values here across this, there's about 800 odd observations here that only have one missing value. But of course, where the missing value is in a different column for each of them, right? So we can't throw columns and rows away in order to try and be left with some complete data. We're going to have to do something about trying to guess what these missing values are in some way. So we're now going to look at the idea of imputation. So imputation is basically predicting what the value is. So this next block is looking at imputing using the mean. So the idea is that all we do is we fill in the age information using the mean of the wife's age. So impute mean. Essentially what that does is it runs through the column wife's age that we've passed into it, and it uses the mean on the values that are there. So it computes the mean, throwing away the missing data, and then it uses that value as the value for where the wife's age is missing. So if we run this, we see that the wife's age now is complete, and it has the mean set to 40.7. Okay. Which was the mean before. Okay. Now, the problem with doing this is we can't then assess what the impact is because we've just overwritten the old wife's age column with the new wife's age. I guess we could name it something else, right? We could do it something like that. And so now you can see that there's the old wife's age column there where the mean is 40.7 and the completion rate is only 85%. And there's the new one. The mean has stayed the same because, of course, what we've done is we've gone and used that mean to fill in the values that are missing. Right, so we've taken those 29 observations and we've set the value to be 40.7. Okay, so the mean doesn't change, of course, because we've just added a bunch of observations at the mean. Okay, now to visualize the effect of this process, what we might want to do is, first of all, we could do this kind of trick, right? So we could, right? So we do this, that adds that extra column there, and then we could plot that extra column versus some of these other ones, maybe against the height age, and then we could color it by whether this one's missing. So for example, we could pump that into ggplot, and we could say do a histogram of the imputed wife's age. Right, so that's what the imputed wife's age looked like. Let's reduce the number of bars. Right, that's the imputed wife's age there. Okay, and we could colour that then by whether the wife's age itself was NA. So we could do the fill. So that's X here, been a bit sloppy. We could fill by is the wife's age NA. Right, so you can see here that here are the ones where the wife's age is missing, and the red ones are the ones where the wife's age was not missing. So you can see here that what we've done is we've just put an additional spike at 40.7, which was the mean wife's age. We've just stacked 29 data points up there. Okay. So let me leave this code as it was, so that it's the same in the solutions. Okay. Okay, now down here we use this additional function bind shadow. So bind shadow, what that does is it basically goes through and creates additional columns, one for each existing column, dictating whether it's missing or not. Okay, so let's have a look and see what this does. Right, so it adds on these extra columns: height, age, NA, husband's age, NA, husband's height, NA, wife's age, NA, and wife's height and husband's age at marriage, and you've got not NA or NA. Right, those two possibilities there. So we can then impute directly into the other variables, because we have these ones telling us whether they needed to be imputed or not. So you can see here, I'm going to impute the wife's age, and I'm then going to do a scatter plot of husband's age versus wife's age, but I'm going to colour them according to this variable here, which tells me that it wasn't NA before imputation and that it was NA before imputation. So it's just a handy way in order to impute using the same variable name, so you're not introducing a bunch of extra variables for the imputed versions of the originals. Instead, you're overwriting the original data with the imputed version, which is going to be useful later on when we do modelling and things. But we're retaining the information as to whether it was imputed or not. And you can see here that this imputation is a bit of a silly way to do things, right? So we've imputed just using the mean wife's age, so all we've done is put the wife's age for all of the missing observations equal to 40.7. But of course, that means that the imputed values don't really follow the same distribution as the underlying data does, because the underlying data had a strong correlation between the wife's height and the wife's age and the husband's age. Okay. So really, we're going to need to do a better effort of a better technique of imputation. So this is what Knearest Neighbors does. So Knearest Neighbor imputation, essentially what this does is, instead of using all of the wife's age data to impute the missing values, you instead use rows that are similar. So for this one down here, say, which is missing the wife's age information, we're not going to use all of the red points here to impute this one. Instead, we're just going to use the red points that are around it. Okay? And what I mean by the red points that are around it is that we know what the husband's age for this observation is. And we also know the husband's age at marriage, and we also know the husband's height and the wife's height. All of those things can then be used to find other rows in the data that look similar to this one. Okay, and it uses some metric, it's called Gowers distance, for computing similarity. So we find the rows that are similar, and then we will use the wife's age at those similar rows. So essentially what we're going to be doing is using these observations down here. Okay, and then we'll take the mean, or the median, a measure of centre essentially, of these observations, so that the wife's age is going to be down near these ones. Okay, so the KNN function in the Vim package is used for this. Now by default, the KNN function also adds those additional NA functions, so it contains a bunch of variables postfixed with imp. So I'll run this to show you what it looks like. So here we have the husband's age, husband's height, the wife's age. You can see that it's been filled in here. That one there's been filled in. And then this tells us whether it was imputed. So you can see here that the wife's age was imputed. So we can use these columns to determine the effective imputation on these ones. So again, we do the imputation just directly on the original data, so that we can then use it for modelling and all sorts of other things. But we have some additional information tacked on the edge, tacked on the side, that we can then use to decide whether the imputation that we've performed is sensible. So we're going to do the same plot above, and we're going to colour it using that column there. So you can see here that this is much more reasonable. Okay, the observations, that observation I was talking about before, has been put down with the similar ones. Now it doesn't always happen. So this one up here, for example, we've imputed a bigger height, a bigger age for it, and that may be because we've used other information other than just the husband's age here, right? We've used the husband's height, the wife's height, and the husband's age at marriage. And all of those things will have gone into deciding where these points are. Okay. Now, when we did this, we used k equals 5, so we found 5 similar rows. Okay, so we used 5 near neighbours to each row to do the imputation. So for each row where the wife's age was missing, we found 5 similar rows where the wife's age was not missing. And then we used those 5 similar rows, the median or the mean of those 5 rows, to do our estimation. Okay, so we're going to play around with k and see what happens. So we'll take that same code block. So we'll try k equals 1. So that would be finding one row that's similar. And essentially we get the same type of thing. We get a bit more variability though, right, than we had before. Okay, so it may well just be that the one row that we found for these ones that are quite dissimilar to the trend, perhaps the row that we've chosen is quite similar to others because they had very similar husband height and wife height. And because the relationships between husband height and wife height aren't as strong with the wife's age, we've used those points because they're the ones that are closest, but they're not strongly informative. So the K-Nearest Neighbors is not using any underlying model to figure out, to select the variables that are more important than others or anything like that. All it's doing is across all of the columns, these 2 rows are most similar, so we're going to use the wife's age in that other row in order to do the imputation. What happens if I increase it a lot to say 100? Then essentially what happens is we move closer and closer to mean imputation, right? And the reason is that we're using 100 other rows. So for this observation down here, we're going to be using essentially the bottom 100 points here to do that imputation. And there's only 200 in total. So if I increase the k enough, say to 200, then I just get mean imputation, right? Because I'm using the 200 nearest neighbours to do, and then which is then every row is a nearest neighbour, and so it's just computed the mean or the median across those 200 rows, which is the same thing we did before, right? So there's some sort of happy spot somewhere between 1 and a few hundred that gives us a reasonable imputation. 10 looks pretty good. Okay, let's have a look at the yeast data as well. So we're going to select out just the columns that start with alpha, just to reduce the size of the data frame that we're going to be using. So we're going to filter, we're going to select, aren't we? Select the rows that starts with alpha. Right, so that just gives us our 18 columns, so still quite a lot to play with. Okay, and then we're going to use k-nearest neighbour imputation on that. So we're going to start with k equals 5, say, and then we're going to take a look at the relationship between alpha 0 and alpha 7 as a starting point. Right, so we're going to feed that into ggplot, and we're going to look at the relationship between alpha 0 and alpha 7. Okay, so let's do that. So we're doing our imputation, and there we go there. So you'll notice that here, because of the massive number of points we've got, we can't actually visualize this very well, and that's really for 2 reasons. One, we've got lots and lots of points, so they're all on top of each other. We could solve that with some transparency. So I could add on some transparency here. Probably want quite a lot of it. The other problem is that the points are plotted in the order that they appear in the data. So the blue points here that are, maybe that's a bit too much transparency. The blue points here are plotted where they appear in the data. So if there's red points later in the data, they'll just be sort of put over the top. So we could first arrange the data by the imputation column, so that the blue points are plotted last. So now we can actually see where they are. So you can see here that, at least in terms of the relationship between alpha 7 and alpha 0, we're not doing fantastically here. But that's perhaps not all that surprising. I mean, at least we're sort of doing better than mean imputation would be, which would be just a straight line straight across. Remember, we do have 18 variables here. So the closeness of rows is computed across those 18 variables. So that it's not computed purely in terms of alpha 0 and alpha 7. Okay, we could try a different k, so we could increase k to maybe 100 or so, see what happens. You can see here that now we're moving closer and closer towards mean imputation. So k probably wants to be a little bit lower than this. So 5 is generally a pretty good number, and I think we'll just stick to that. Oh, there it goes. K equals 1,000, 1 and 1,000 as well. Let's do those just to see what happens. So let's do one for k equals 1. And one for k equals 1,000. See what we get. Okay, try again. Seems that my computer's having issues. I think I need to restart. It installed a bunch of stuff, including kernel headers and so on earlier, and I suspect it's sort of half updated. There we go. So k equals 1,000 is very close to mean imputation. K equals 1 is a little bit more, we've got a lot more spread. The problem with choosing a very small number for k is that we're only using the information from one other row, and hopefully that row is going to be informative. But it means that from sample to sample we're going to have a lot of variation, so there's going to be a lot of uncertainty there. In each of these imputed values there's going to be a lot of uncertainty because we're only relying on one other row in the data for that imputation. Whereas for k equals 1,000, there's not much uncertainty because we've averaged across 1,000 observations. But of course we're not getting a very good estimate of what alpha 7 is, for example, because we have averaged across too many observations, right? We're using observations that are very, very far away from the one that has missingness in it in order to contribute to the value that's missing. So essentially we're averaging across all the data. We might as well just about be doing a mean imputation for that one. So somewhere between these two extremes there's sort of a happy medium.